All right, guys, welcome to our lesson. We're going to be talking about ideal gases, that is, gases that are under conditions where you can use, you guys remember that's called the universal gas law or the ideal gas law. Remember, there's four factors that affect a gas: pressure, volume, number of moles, and temperature. So we're going to look at that. But anyways, this guy says, we got our own way of solving things around here, mister, and it don't involve tights and capes. Superheroes of the Old West. Yeah, I don't think they would do well in the Old West. They didn't take kindly to people in tights, especially men. Okay, you guys, we're going to start with a concept called Dalton's law of partial pressure, and it states the total pressure of a mixture of gases. You guys remember, most gases that you're going to encounter are going to be mixtures, equals the sum of the pressures that each would exert if it were present alone. You're like, what the heck does that mean? So it's kind of like, if you guys think about a mixture of gases, what could you guys think about? The air. You guys know the number one component of air is nitrogen, and then there's some oxygen and carbon dioxide and even some water vapor. So basically, what this is saying is if you were to take oxygen alone, it would exert a certain pressure, because you guys know the gas molecules are moving, they're hitting the walls of the container, hitting the walls of the room, that's exerting a pressure. Now, for example, nitrogen accounts for like 70% of the air. So if it accounts for 70% of the air, so 70% of all the molecules in the air are nitrogen, it's going to account for 70% of the pressure. Oxygen accounts for maybe about 20% of all the air molecules. It's going to account for about 20% of the pressure. What this is saying is, to get the total pressure, you just sum up the individual pressures. So you guys, it's a pretty simple formula. Check it out. So if I want to get the total pressure of a mixture of gases, I take the pressure that one gas would exert by itself, plus the pressure that another gas would exert by itself, and then so forth. Okay, so write that down. So here's a typical problem, AP problem. So let's say, so we're performing a reaction. I think we're heating up potassium chlorate, and so we're going to generate some oxygen gas. Okay. So when one collects a gas, and so you see how you could collect the gas, you'd have this inverted beaker, and then it's filled with water, and then gas is less dense than water, and so it's going to collect up here, and you can trap the gas, and you can see eventually you have a total. You have your gas in here. You can see as the gas collects, the water is displaced, and then ultimately, when this thing stops moving, what can we say, right? The level here is going to be equal to the level here. The total pressure of the gas inside here is going to be equivalent to the atmospheric pressure. So here's a question. What is the pressure of the collected gas? So remember, we're collecting, let's say, oxygen gas. We want to know what pressure is oxygen gas exerting. If the vapor pressure is 120 millimeters mercury, here's a little introduction, guys. You guys notice that the gas collected here is over water, right? Well, what's some of the water doing? You guys know some of the water is overcoming its intermolecular forces, holding the water molecules together, and it's evaporating. So you do actually have some water vapor in there. And that water vapor, white gaseous water, those are moving around independently. Those are exerting a pressure. That's what we call the vapor pressure. So the pressure due to the evaporated water, and that changes based on temperature. You can imagine the higher the temperature, the more evaporates, the higher the vapor pressure. So at this temperature, it's exerting that pressure. So knowing that, what is the pressure of the gas that the gas itself is exerting? And it says it's at standard atmospheric pressure. So here's how you would do it. Right? When you guys agree, well, we would know that the total pressure in here is equal to the atmospheric pressure, right? Because the water is no longer moving. If this pressure was higher than this, the water would still be moving down, right? And if this was higher than that, that would be moving up. But eventually it's going to reach an equilibrium, so we know the total pressure is, and then the question is, what can I set up? Well, if the total pressure, I know P total is equal to the pressure of the atmosphere. And let's say it's standard atmospheric pressure. I think I said that, yeah. You guys, standard atmospheric pressure is 1 atm. Or you could say it's 760, we might as well put it in millimeters of mercury. You guys remember this was an equivalency, these are equal. So that's the atmospheric pressure. But what was the P total? You guys remember what's in here? What's over the water? Not only the pressure of our gas, but also, wasn't it the water pressure? You know, the vapor pressure. And what was the vapor pressure? We said it's 120 millimeters of mercury. So if I wanted to get the pressure of the gas, what would I do? You guys got it? When you just subtract 120, right? So what's the pressure of the gas? 640 millimeters of mercury. You guys see, this is an application of Dalton's law of partial pressure. You just add up all the individual gases that make up your mixture. All right? So that's what it's saying. It's saying you just subtract. Kinetic molecular theory. You guys, the reason why it's called, we could break this down. What is kinetic? Kinetic has to do with movement, right? Molecular, we're talking about the movement of molecules. Why do we call it a theory? Because we can't directly observe molecular motion. We know air molecules are moving around even though we can't directly observe that. Okay, so we call it a model. It helps us to explain things that we might not otherwise be able to see. So there's certain, they call them tenets of kinetic molecular theory, okay? One is that molecules are moving randomly. Okay, so you guys write that down. I purpleized that. I don't know if you guys can see the color. Molecules are moving randomly. Okay. Remember, this is all within a gas unit, so we're thinking about, gases. The molecules are relatively free to move, as opposed to like in a solid or liquid situation, right? Second, the combined volume of all the molecules of the gas is negligible. So what we mean by that, guys, is the volume that the molecules themselves take up is so insignificant you might as well not even count it. Like, I'm in this large room. I don't know, some of you guys have been in my room. I'm in the same room. It's a pretty large room. If I were to take all the gas molecules, you think about it, all the nitrogen, oxygen, N2, O2, CO2, H2O, take it, you know what? It would probably, the volume it would take up would probably be equivalent to the tip of my pencil. You guys remember, once again, what does that tell us? Man, atoms, molecules, they are extremely small. What's taking up most of the room, the space in this room? It's just empty space. Those molecules are moving around. So the actual volume of the molecules themselves is negligible. That's what that's stating. The third tenet, the attractive and repulsive forces between gas molecules are negligible. So this is under conditions of like ideal conditions. So when we want to use the universal gas law, this is true under ideal conditions, and that would be assuming some of these tenets. Molecules are moving randomly, the volume of the molecules themselves is negligible, and also the attractive forces. And in reality, here, for example, think about, water vapor. Along with my hot, funky breath, what am I breathing out? Carbon dioxide and also water vapor. That's why when you breathe on a mirror, you're going to see fog, right? So this is saying that the water molecules themselves, when they're moving around, there is no attractive forces, and that would explain why when they come out, there's elastic collisions, and so they bounce off with the same amount of energy that they started. That's what we're saying. But in reality, we'll talk about that. Okay, and then lastly, average kinetic energy of the molecules does not change with time as long as the temperature of the gas remains constant. Okay, so what they're saying is the only thing that affects the speed, the velocity of those molecules is the temperature. If you maintain a constant temperature, those molecules are going to be moving at the same speed. This is kind of interesting. Check this out. So this is a curve. It's showing the molecular speed. So like in a sample of gas, remember when you guys are thinking of a sample of gas, just think of like a balloon filled with air, right? And so what we're saying here, like let's look at 100 degrees. At 100 degrees, some of the molecules are moving slow. You see, this is speed, and this is the number of molecules. Some of them are moving slow, some of them are moving really fast, and the vast majority are kind of moving in here. And you guys remember, what we do is when we record the temperature, that's the average kinetic energy of the molecules, so it's the average. But now you look here at a lower temperature, you see you still get the curve. You still have some moving fast, some moving slow. But you notice at a lower temperature, the molecular motion, the range is shortened. You're going to have a steeper slope at a lower temperature than a higher temperature. So at higher temperatures, you're going to have more of a spread. That's just kind of interesting. All right, moving on. Okay, here's another term for you guys. You guys got a bunch of terms. AP Chem. Effusion. Effusion is the escape of gas molecules through a tiny hole into an evacuated space. So just imagine you got a container, you got a hole. When you guys agreed, just due to random molecular motion, some of those molecules are going to escape through the hole. The rate at which they do that would be the rate of effusion. Okay? So why does a balloon eventually deflate? You guys know when you guys have a party of balloons, eventually you can leave it there, eventually it deflates. You guys know why that is? Do you think it's because the molecules after a while finally get, they're bouncing around and they're like, right, that's what's causing the walls of this, the balloon to be inflated. Do you think the molecules get tired after a while? Like, man, I'm tired of moving around. And then they just stop moving and then it kind of deflates. That's not true. You guys remember, the third tenet of kinetic molecular theory is that the molecules do not lose energy. What happens is there's actually tiny pores, because that's a fancy word for holes. There's tiny holes that the molecules eventually escape out of, right? And you give enough time, all the molecules will escape. Here's a question. Which balloon do you think will deflate faster? One filled with nitrogen, like let's say I filled it with nitrogen N2, or one I filled with helium? What do you guys think? Well, to answer this, you kind of have to think, well, they kind of showed the answer there, but what's different between N2 and helium? What would you guys think is different? Well, if you look at the periodic table and just kind of think about it, isn't it difference in size? N2, nitrogen weighs 14, if it's diatomic, it's 28 AMU. Helium only weighs 4 AMU. It is much smaller. So what do you guys think? What do you think is going to deflate faster? When you guys predict the one with helium, and why is that? Well, smaller molecules, what do? They move, oh, you might think smaller molecules, they can escape through the hole easier. Okay, I can see that. But also they move what? The smaller the molecules, just think about it, guys, on a track. I hate to say it, but think about it on a track team. Who's going to move faster, the skinny guy or the fat guy? It's going to be the skinny guy, right? Smaller molecules can move faster, and therefore they're going to effuse out of the holes faster. Therefore, you would expect the helium gas to deflate fast. Oh, and you guys can see this here, right? You can see the helium balloon. This is originally, helium balloon here is much smaller than here, indicating those helium atoms effused out much quicker than they did with nitrogen. You see how the nitrogen balloon is pretty much the same? Okay. That's what we said. Okay, and diffusion just talks about how, right, when if I were to pop this balloon, what's happening, the molecules of the gas in the balloon are just going to spread out from an area. In this, they're like more highly concentrated, let's say this carbon dioxide, and they're going to just randomly diffuse out to areas of lower concentration. So that's slightly different than effusion, which is the movement through a small hole. He says, Your Honor, I need to be removed from this jury. You guys being on the jury is pretty cool. During the last recess, I saw the defendant by the snack machine. She was eating some diet muffins labeled guilt-free. I think you might be swayed by that. All right. You guys, here, I write this, you know what, we're going to, this is kind of confusing, right? It says, under ideal conditions, the relative rates of diffusion for two different gases is inversely proportional to the square root of their molecular weights. You guys, normally, if you guys were in class, I'd get bonus points if somebody could kind of translate this into a mathematical expression. You know what, we're just going to do that. So we're going to just do that right away. So here's Graham's law. You guys write down Graham's law. Here, and you guys don't really have to write this, but here, we're talking about two, it says, the relative rates of diffusion for two different gases. So here's what I'm going to do. I'm going to make up a formula. Rate, I'm going to say rate of gas 1 compared to rate of gas 2, the rate at which it, fuses out of a hole, or diffuses, is equal, it says, notice it says, inversely proportional to the square root of their molecular weights. What? Well, oh, I see there's a square root in there. But you notice it's inversely proportional. So if this is rate 1 to rate 2, inversely proportional to their molecular weights, what I would do on top is the molecular weight of gas 2 over the molecular weight of gas 1. So what I did was I translated this into a mathematical equation that we could then use. Okay, you guys, we're going to solve one. Okay, so here's the question. It says, as oxygen escapes from a container, so just imagine a container with a small hole, oxygen's escaping. The pressure, you can imagine, as you have less oxygen, the pressure is going to drop, right? The pressure drops from 2,000 to 1,000 torr. Remember, torr is another word for millimeters of mercury. Okay, these are just different units we could use, in 25 minutes. When an unknown gas escapes, the pressure drops from 2,000 to 1,000 torr in 30 minutes. What could be the unknown gas? You guys, even before we punch any numbers, I would expect you guys, my AP chemistry students, to be able to predict something about the gas. What do you guys think you could predict, something you could predict about the unknown gas? The gas that we know about is oxygen. What could you guys predict about the unknown gas? I'm hoping you guys put a pause here and you're like, What you could predict is, must it not be, what can we, shouldn't it be heavier than the oxygen? You guys see why? Because look, pressure dropped 1,000 torr in 25 minutes. This dropped 1,000 torr in 30 minutes. You can see this molecule is moving slower. And why is it moving slower? Because it's heavier. So therefore, I better get, let's say I can calculate the molecular weight of this, I better get a molecular weight that's heavier than the molecular weight of that. And that's a good way I could potentially check myself. Okay, so we're going to set up our equation, rate 1. So I'm going to call my gas 1 oxygen. And what's the rate? You guys, rate is always an amount per time, right? So an amount is, it went from 2,000 to 1,000, so what? It dropped by 1,000. When you guys agree, 2,000 minus 1,000, 1,000. So it was 1,000 torr per 25 minutes. When you guys agree, that's a rate 1. You guys see what I did? I take rate 1 and I divide it by the rate of gas 2. And what was gas 2? It dropped, it went down 1,000 torr, and it took 30 minutes. Okay? And then that's gonna equal to the square root. You guys remember what we're gonna do? We're gonna do the molecular weight of gas 2, which I don't know, so I'm gonna just put, whatever my unknown gas is, and then I'm gonna put over the molecular weight of my the gas I know about. Oxygen, look at your periodic table, it weighs 16. If it's O2, it weighs 32 grams per mole. Okay, so when you guys do the math here first, when you do the math, essentially, you guys know how this works, right? A fraction divided by a fraction is a fraction multiplied by the inverse of the fraction, so the thousands will cancel out, and essentially I'm going to go 30 divided by 25. I know if you didn't pick that up, punch it in the calculator the way you feel comfortable, but it's 30 divided by 25, and what I'm going to get is 1.2 is equal to this. You guys, what would you do at this point? When you guys get rid of the square root sign by squaring both sides, right? So then I'm going to square this. And you get 1.44 is equal to the molecular weight of gas 2 over 32 grams per mole. And then when you guys solve for this, when you multiply both sides by 32, then I take that, multiply it by 32, and I'm going to get 46. So I just figured out that my unknown gas weighs 46 grams per mole. You guys, that helps. I should feel pretty good about that, because what did I predict before? Didn't I predict that my unknown gas should be heavier than the gas I knew about, which weighs 32 grams per mole? So then I could speculate, what could the gas be? It's 46 grams per mole. Could it be neon? No, neon weighs 20 grams per mole. Could it be argon? Argon weighs about 40 grams per mole. I might have to think, you guys, most of the things exist kind of as compounds, right? And I'm thinking, oh, you know what? Could it be NO2? Nitrogen weighs 14. Each oxygen weighs 16. You guys think about it. 16 and 16 is 32 plus 14 is 46. Oh, maybe this is nitrogen dioxide. All right, typical kind of Graham's law problem. Okay, guys, almost done. That's it for the calculation, so you can breathe this sigh of relief. Won't have any more calculations. Almost done. Okay, so now look at this. It says, this is kind of an interesting chart. It says the behavior of gases only conforms to the ideal gas equation at relatively high temperatures and low pressures. Okay, so what this is saying here is, it's saying, for example, you guys know if I had a sample of gas, let's say I had 1 mole, if I had 1 mole of a gas, right? Well, I should be able to use Pivner, right? I should be able to, let's say I have a sample, let's say I have 1 mole of a gas, I should be able to plug in the pressure that gas is exerting, the volume that it's occupying, and the temperature which it's at, and then I plug in, you guys remember R is the universal gas law constant, it's 0.0821 liter atmosphere per mole Kelvin, and then I plug that all in, and if I have 1 mole, I should get a 1 here, right? That's what this is showing here. If I plug in all the values, I should get a 1. But now this is showing various gases at various pressures, and you can see none of them really hits where it would predict correctly that you would have 1 mole of a gas. So, and you guys can see, where is the greatest deviation? Where is where do these more greatly deviate from the 1? And you guys will notice, right, because here's the 1 right here, right? Where they deviate the greatest is when it's at higher pressures. So then I have a question. What do you guys think? What might account for the fact that the gases don't really behave in an ideal way when it's at high pressure? And to answer this question, you have to look back at remember those 4 components of kinetic molecular theory. And I would ask, which one of those assumptions would not be true under conditions of high pressure, where you can see there's a big deviation? You see these are way off of 1, which is what you should be able to calculate if you inputted the correct pressure, volume, and temperature. So what do you guys think? High pressures, what one of those kinetic molecular theory tenets would not be true? Okay, now here I hope you pause it and go, you look back at kinetic molecular theory, what you wrote down, and go, which one of those would not be true? Okay, so assuming you're coming back to me now, what would not be true? You think about under high pressure situations, right? Wouldn't you guys agree to have a high pressure, wouldn't you have to have a lot of gas in a small confined space? Well, if you have a lot of gas in a small confined space, just think about, right? If I take the gas molecules and I put them in a smaller space, the pressure increases at a high pressure. Which one of those tenets would not be true? Remember, it said that the volume of gas molecules is negligible. Well, you think about it. Under extremely high pressures, look at this, at 1,000 ATM, you guys know the atmospheric pressure right now, now we're under pretty standard conditions, it's about 1 ATM. So if we magnified that by 3 factors at 10 to 1,000, we're talking, it's just so compact, the gas molecules are so compressed that now, given that space, the volume of the molecules now would not be negligible. They would be somewhat considerable, when you guys agree, if you had a whole bunch of gas molecules confined to a smaller space. So, because the tenet of kinetic molecular theory would not be met, therefore you would not expect a gas at high pressure to exhibit ideal gas conditions, and therefore you really could not apply Pivner. You guys get what I'm saying? You wouldn't be able to apply the corresponding high pressure, volume, and temperature, and let's say you have 1 mole, and very rarely would you would deviate greatly from 1 mole. Let's see another condition in which you would not meet ideal conditions. Guys, look at this. So once again, we have the same thing. Once again, let's assume we have 1 mole, let's say we have 1 mole of a gas. So basically should all equal here, okay? But under what conditions do you guys see here where there's the greatest deviation? So this is 1 mole. Where do you see the greatest deviation from 1 mole? We already talked about it, high pressure. You guys see that? We already talked about high pressure. But then also, now look at, they're comparing 3 different gases. This one's at 200 Kelvin, 500 Kelvin, 1000 Kelvin. Where does it deviate the most? Where when you calculate, you're going to get a number, like for example, if we did this one, and we calculated how much gas is present, even if there really was 1 mole of gas, if you plugged in the values into the Pivner, you would get a number that's like 2.8. You can see that would be under conditions where the temperature is the lowest. You see, when the temperature is the highest, you see there's still some deviation because we're at high pressure, but nonetheless, it's closer to the 1 mole that I would expect. So now, I want to ask you the same question. What might account for the fact that gases at low temperatures deviate greatly from ideal gas condition? What do you think? What part of kinetic molecular theory would not be true? What one of those assumptions would not be true at low temperatures? You think about it, at low temperatures, gas molecules are moving what? Very slowly. You think about it. When they're moving very slowly, what's going to be the result? Think about this as like, say, water molecules. When water molecules are at high temperatures, they're moving around fast, and what would you guys expect? When they hit each other, no attraction, right? No attraction. But now, if they're moving slowly, you guys remember, there's attraction between protons and electrons of atoms in one molecule for that of another. That's what we call intermolecular forces. When the intermolecular forces have greater impact, and therefore if they're moving really slow, when they contact each other, now they might collide and then bounce off, but what would happen, wouldn't you guys expect them to kind of lose energy due to the attractive forces holding these together? So therefore that also would not meet ideal conditions. So when will you have ideal conditions? When can you really use Pivner in situations? When you have what kind of pressure, guys? Low pressure situation, because that means gas molecules are spread out, and under high temperatures, because then molecules are moving fast and they can easily overcome any intermolecular forces. All right, guys, I think that is it for today. Thanks for joining me. We'll see you guys next time.